Welcome to today's Explainer. We're diving headfirst into a really fascinating clash between two incredibly powerful ways of making decisions. On one side, the cold, rigid, absolute mathematical perfection of artificial intelligence, where literally every single parameter is engineered for peak performance. On the other side, the chaotic, messy, and seemingly completely irrational world of biological evolution. We're going to look at how AI optimizes its choices and then flip the script to look at what researchers called the crazy love of nature. It's a wild ride, so let's just jump right in. Here's our roadmap for today. We'll start with the quest for optimization, move into AI's perfect scaling laws, and then pivot to nature's messy cocktail party. After that, we'll break down the rules of irrationality, explore the biological decoy effect, and wrap it all up with engineering versus evolving nature. Let's get to it. Section 1, the quest for optimization, maximizing limited resources. So whether you're a computer scientist building some massive neural network or, an animal just trying to survive in the wild, you're facing the exact same fundamental problem. How do you make the absolute best choice when your resources are strictly limited? You can't have it all. To understand how we do this in the digital world, we really have to talk about the compute budget. In AI, researchers don't have infinite time, they don't have infinite supercomputers, they have a very specific compute budget. The real challenge is figuring out exactly how to balance the size of the AI model, like how many parameters it has, with the sheer amount of training data they feed into it. Because if you get this balance even a little bit wrong, you're wasting millions of dollars on a totally underperforming model. Section 2, AI's perfect scaling laws, the chinchilla breakthorn. Now, a team at DeepMind was looking at how these massive language models were being built, and they realized the entire industry was making a huge systematic mistake. Everyone was just scaling up the size of their models, adding more and more parameters, but keeping the training data pretty much the same. But the DeepMind team proved that optimization actually follows this beautifully rational mathematical scaling law. Look at this comparison. It is staggering. You've got these massive earlier models, right? Gopher with 280 billion parameters, Megatron Turing with 530 billion. But then there's DeepMind's compute optimal model, Chinchilla. It only used 70 billion parameters. So what was their secret? They trained it on 4 times more data. They discovered this incredible rule. For every doubling of model size, you have to double the training tokens too. By simply optimizing that ratio, this much smaller model literally blew the giants out of the water. And the result of all that optimization, a massive 67.5% average accuracy on the MMLU benchmark. I mean, that is a full 7% improvement over the much larger Gopher model. What this proves is that in the sterile, perfectly engineered world of AI, scaling size and data equally is flawlessly rational. The math just works perfectly. Follow the formula and you get optimized results. So AI relies on this flawless mathematical rationality. But you've got to ask yourself, is perfect rationality really the only way to optimize? What exactly happens when we unplug, leave the pristine air-conditioned data center, and step out into a world where the rules aren't written by code, but by survival, predators, and chaos? That brings us to Section 3, Nature's Messy Cocktail Party, the Tungara Frog. Let's take a trip to a noisy, incredibly high-stakes pond in Panama to look at the biological reality of decision-making. And let me tell you, it is far from perfectly rational. To find a mate, this little male Tungara frog has to sit in the dark and call out, but there's a huge catch. The fringe-lipped bat is actively eavesdropping on those exact mating calls to find its next meal. So talk about a high-stakes environment. This frog has to be loud and attractive enough to win over a female, but not so conspicuous that he accidentally invites a bat over for dinner. To pull this off and attract females, these male frogs have evolved a pretty complex acoustic strategy. So a simple whine sound is enough to get a female's attention. But when a male follows up that whine with these complex little chucks, females go crazy for it. They actually show a massive 5-fold preference for him. But here's the tragic irony. The eavesdropping bats, they prefer those complex calls too. This entire setup creates a massive cognitive hurdle for the frogs, something we call the cocktail party problem. Think about being at a super crowded, really noisy party, and you're trying to focus on just one person's voice across the room. It's tough, right? Well, the frog chorus is exactly like that. For a female frog to choose a male making that sexy, complex call, she has to correctly match the right chuck to the right male's whine, while surrounded by a literal wall of overlapping sounds. It is a wildly difficult cognitive processing challenge. Section 4, the rules of irrationality, Weber's law in the wild. So how do animals even process these complex signals? Well, it turns out biology does not use the absolute precise math that our AI models use. Instead, biology relies on proportional heuristics. See, rational economic choice, which is how we assume machines and logical systems operate, evaluates absolute differences. It's very black and white. But biological cognitive bias operates on proportional differences. This is a concept known as Weber's law. Basically, it means that as the size or intensity of a stimulus increases, the difference between two things has to be significantly larger for a brain to even notice it. It's a biological shortcut. And what's really fascinating is that it actually puts a speed limit on evolution for extreme traits, simply because the choosers stop noticing those minor absolute improvements. When researchers actually tested whether female frogs preferred calls based on the absolute number of extra chucks or the proportional difference, the data was super clear. They follow Weber's law. In fact, proportional difference explained 84% of their preference. But okay, here is the truly mind-blowing part. The frog-eating bat? It uses the exact same cognitive algorithm. Both the frog, who's just trying to find a mate, and the bat, who's just trying to get a meal, are locked into using the exact same irrational biological heuristic. Moving to Section 5, the biological decoy effect, irrational economics. Let's look at another way biology completely throws economic rationality out the window, especially when choices are being made in a dynamic social context. Consider this really famous experiment on human behavior using magazine subscriptions. When people are given a choice between a web-only subscription and a more expensive web plus print combo, the preference split was 68% to 32%. Pretty standard. But when they introduced a completely terrible decoy option, a print-only subscription for the exact same high price as the combo, human preference wildly swung to 84% favoring the combo. The mere presence of a totally inferior decoy completely altered their perception. From a strictly mathematical standpoint, this completely violates the rational axiom of regularity. And guess what? This exact same irrationality happens with our frogs in Panama. When given a straightforward binary choice between call A and call B, female Tungar frogs show absolutely no clear preference. It's a coin toss. But the moment you introduce a third, clearly inferior call C as a decoy, suddenly the females develop a strong, definitive preference for call A. Just like us humans getting tricked by a magazine subscription, the frog's economic choice is incredibly malleable and heavily influenced by social context. Finally, Section 6. Engineering versus evolving nature, the grand synthesis. We've just seen two completely different approaches to navigating complex information and dealing with limited resources. But the crucial takeaway here is this. Biological quirks aren't bugs in the system. They are highly tuned adaptations for surviving in insanely noisy environments. DeepMind's chinchilla model achieved its perfection in a sterile, perfectly controlled laboratory. But the Tungara frog? It operates in a muddy pond full of predators, noise, and harsh metabolic limits. What a computer scientist might dismiss as irrational is actually biology's brilliantly messy way of staying alive. Which leaves us with a pretty big question. As artificial intelligence continues to leave the pristine laboratory and enters our incredibly messy, totally unpredictable real world, will pure mathematical optimization be enough? Or will our perfectly rational machines eventually need to adapt and maybe even adopt the irrational survival heuristics of a little Panamanian frog? Thank you so much for joining me for this explainer, and remember to always keep questioning the data around you.